Okay, so we have another number here. And sorry to be a little bit more formal, but I'm for standardization. And somehow the title creeped a little bit, so I'm on standardization. But I'm also on research. I was part of Fortis, and I'm also on the practical side. So I'm one of these consultants that help you doing things the right way, doing ASPICE, doing functional safety. And maybe one of my famous works you have already read, it's entitled ISO 26262. I was part of the first team doing it. So I know a little bit of this. And I was doing functional safety and AI for a long time. And then I thought, okay, we need to combine this. So how to do it safe in systems engineering. So now again, a number. All these numbers are meaningless. Ours are not. So 28 is, I couldn't help it, 28. And this was the area we were working in the VDE, DKE, in the working group. But of course, all of you, or at least 90% know 42, right? Hitchhiker's Guide Through the Galaxy, it's the answer to all questions, or standing for AI, you know, the subcommittee in the ISO 42, right? And what again is 6.1? Any idea? 61508, what was that again? So this was the one we were looking at when we designed the standard. So we will talk about functional safety, and even more, we call it trustworthiness, which is a meta term including safety, also cybersecurity and other stuff. So I don't want to bore you. We know AI is on its way, and we are all struggling with the question how, not if. And famous guys from Bosch, from others told us there will be scarcely no product without AI in maybe 10 years. This is not 10 years ago, but we have all the Gartner hype cycles with AI, and we are now actually driving this. So what happens if you apply AI? Maybe this. This is a more or less famous situation where a car needs to detect traffic lights, and there are these nice co-op flags, and there are traffic lights detected. So seems to be some failure. Maybe missing craftsmanship, I don't know. But there are other failures. We saw this request, please, DALL-E, generate me a salmon swimming down a river. And might be this is some social criticism here, I don't know, because of our food and what we eat, but I think it's just a failure. And even some problems with anatomy. Actually, AI, meanwhile, can do better, but we will still find such things, always. We will try to find the explanation why. So in the end, there's a lot of mysticism around. So we do things with AI and somehow it works, and we still, at least from research, do not understand why, but it's fine. It's speeding up time to market. And let's turn this mysticism into safety, trustworthiness. So for this, we need to understand about these AI technologies, this new cool thing. Looking into the past, we had mechanical solutions. When I was born and even before 1970, most of the products were mechanical. I'm even in some industries, defense, that tell me we can use the electronics, but we better do it in mechanics. Yeah, I understand. Then a lot of electronics came up. Things became smaller, became faster, more efficient. In software, they became even more changeable. And then AI came up. We had some, let me find the pointer. We had some hype, starting hype, an AI winter. And then now the curve is going up. So what is the cool thing about AI now? A lot of stuff. But for me, as a more formal guy, and I love reading PDFs, it is the possibility to implement implicit requirements. You show a little bit of a cat, and it does cats. Something like this. But of course, it is a new technology. And I call it a third kind. Of course, we have a lot of more technologies, but why third kind? If you remind yourself, the overview of the 26262 ISO is hardware, software, and now we have AI. And why is it a third kind of technology? Because it needs its own structured approach, V model, and it has its own fault models. And this is the core what I want to tell you today. So, but still, do we have the means to use AI safely? And I would say yes. Why? Because we have this risk-based approach, our reference safety lifecycle. You all know it. And what do we do there? We have a certain kind of traceability. We want to know what are we doing? So what is the problem with it? And what are we going to do about it? And then we go into the technology, system, hardware, software, and there's a missing box for AI. So, and this is the basic approach of the risk-based scheme. And the idea is to understand bottom up from the hierarchy of the system, what exactly are my faults? So I have a part in it. How can it fail? What is a fault and how can it fail? So in terms of resistor can break or shortcut. And this has a cause-consequence chain up to the next level of the hierarchy design and up to the car, up to the, we call it solution. So this is everything around the car, including the user. What we build is a black box. We will come to this. So, and what is the basic or the secret about functional safety here? The secret is to avoid systematic failures and to mitigate random failures. Okay, how do we translate this for AI? For hardware and software, we know it. We have to design it carefully according to the processes, and we have to mitigate random failures. This again is a little bit of voodoo for some of us, but it's possible. So let's check how we do this for AI. We need this structured approach. Overall, we have this life cycle. We need the fault model. We need to understand what exactly is the problem with AI. And we need a structured approach to evidentially build the AI, hopefully without or only with known failures. And then we can come up with safe or even trustworthy AI. So how are we going to do this? The first is to understand what exactly is the problem with AI? What are the fault models of this third kind of technology? Let's look into the development cycle very roughly. I sketched here for when you develop a neural network, 2 dimensions of inputs, or 2 dimensions, it's inputs and outputs. I don't have the hyperspace here in real, so but just let's regard these 2 dimensions. And what our neural network is doing is depicted by this circle. And this is a general concept, say, of a pedestrian or traffic light or whatever. So this is to be implemented. This is what we want. Then the developer comes in and thinks of certain characteristics of this element, and there's already a small creep because maybe he doesn't think of certain people, certain maybe wheelchairs, and he doesn't regard pedestrians or wheelchairs as pedestrians. Then there's some implicit concepts in the training data, in the data sets. Again, some creep. There can be optimally be learned, again, a creep in this from these data sets. But this is only if we have infinite time and calculating resources. So the actual concept that has been learned is again some shift. So there's this bow from what I wanted to do, what was intended, to the actually specified and to the implemented. And we see a lot of problems here. So we see things that have not been regarded as, in this case, traffic signs. There is research where from the data sets, some funny things have been learned. So here is a quite old publication, but if you have a neural network that detects firmly the traffic light, here it's a green one, but if you change this one pixel, everything switches to red. And in this case, even the other way around. And of course, you have these adversarial attacks and a lot of other stuff. So there's two categories. Systematic failures, yeah, you have to think of stuff and look at and put it in the data set, and some failures due to characteristics of the technology. You do not know actually what has been learned. So I do not want to bore you doing learning. All of you know this is not an exact thing. This is an approximation. We try to find some optimum. Never know if you really get it. The problem is it is not exact, and we don't know where exactly in the landscape we are. Another one, again, something like overfitting. If we try to get accurate, it's a problem. If we have low accuracy, we can have good generalization. And maybe if we have in this pictures from flower, bush, child, woman, man, skateboarder, cyclist, we have the wheelchair here, and we want to have higher accuracy. Might be that our polynomial typed classifier, it's kind of a polynomial, is swimming around and not hitting the wheelchair as true pedestrian. So we all know this. The consequence is that accuracy is no measure for functional safety, but we know all this. What might not be too much known is this hyperblob stuff. So what we at Fortis detected is that if in this hyperdimension, this blob is what a classifier, for example, represents. So this is pedestrian. Yeah. What we detected is that when you analyze this hyperblob, it has holes into the center, a lot of holes. So like this, you can go into it. You can go into this hyperblob and generate pictures that for us are not distinguishable, but for the neural network are clearly not a pedestrian, but for us it would be. So why is it so a problem? It is a problem because it enables something like black box attacks. Why? For attacks, attacking neural network, you want to find these funnels. And this is easily done, going on the surface, looking for a deep point in this hyperspace. And what we also found is that these funnels, not all, but if you take any neural network trained by any data set, doesn't need to be the same ones. They have similar funnels. So you grab some random networks from the internet, pre-trained, look for these funnels in 2 or 3 of them, and you are very probably hitting a funnel in the attacked black box network. So there are a lot of cool things with neural network. We do not understand everything. I do not just want to emphasize it. What we also don't understand is the very top level of neural networks. So how do we apply them? Just let's think of a network that distinguishes dogs and muffins. So it's an easy job. Nice dog, nice muffin. And so how would you say should the performance be of such a network? What is the human performance? What is your performance? Just take a quick look at these guys. Which are dogs, which are muffins? Quickly. So the problem is ethics in the end. It's engineering and ethics. So which performance do we need in autonomously driving cars? Yeah? It is some uncertainty. It is not determinism. Neural networks, of course, are deterministic. So I just read an article, the first non-deterministic computers, but whatever we have, if it's NVIDIA chips or whatever, it is deterministic. Means same input, same output, even the same way how it is calculated. But there's some uncertainty. By the way, there are cool standards on uncertainty coming up. Yeah, I will come to this. There's uncertainty because if you have a new pattern, you do not know if it's going to be detected, predicted as dog or muffin. There are other characteristics of neural networks. In the end, neural networks are some kind of automation. And funnily, we have this guy, Billings, very old paper talking about problems of automation. Read it. It's really cool. There are all the failures the aviation industry did. We can refrain from it. Anyways, so I was talking about failures, systematic and random failures. Systematic capability is something we can somehow measure or claim. The systematics of hardware and software. And what we do is to have culture, experts, quality assurance processes, design methods, proven designs, and so forth. And we can have it for hardware and software. And random, of course, is not in software. Either the fault is in or not. It doesn't change. But for hardware, we have this. We have message and thresholds for it, say failure fraction, or in automotive domain and the 262x2, it's even advanced single point fault matrix, latent fault matrix, and so forth. Sorry, I should have changed this. But it's the same for all standards, so just disregard. But what do we need to do for AI? Of course, AI is running on top of software, on top of hardware. There's some platform, fine. But do we have more? And yes, of course, we have more. We have, of course, a systematic thing we have to consider. We do this with a structured approach, V-model-like. And the other one is uncertainty-related failures. This is a new class. This is only for AI. We tried in the standardization to put it here, to put it here in terms of random failures in the AI, but this is not applicable. We might discuss afterwards with a beer in our hands. Anyways, we have to follow this structured process, consider these uncertainty-related stuff, and have our evidences for the safety argumentation. It's as easy as this. Unfortunately, quantifying uncertainty in neural networks is kind of research. So there are a lot of models, uncertainty models, many flavors, a good survey paper, you can read it, and George Box saying applies. So all models are wrong, some are useful. Depends on what you do. Anyways, industry needs something they can get hold of. And there was this Dean spec, which tried to give you some understanding it. There are further standards, and especially even in the 8800, there's some of it in it. And I just can invite you to join this working group at the DKE. We will do AI and functional safety, and especially currently care about uncertainty. There will be a new standard on uncertainty. This guy. It's tricky. However, there are approaches, details later, maybe with a beer. We need to look at the structured approach. The structured approach is like a V model. It's not a V model in its former sense. Why? We cannot trace requirements down to each neuron. This is not possible, at least not today. And as all these models grow, it won't get easier. But we can do a lot. We have more knowledge than nothing. We can prepare our data. We can check, is it really covering our operational design domain? Is the coverage and the density enough? There are metrics to calculate. Of course, it's a little bit of work. It's not like showing cats, it does cats. It's a little bit of traceable work. You have to care about your design. You implement your loss function, need to adhere to the trustworthiness or safety requirements. You have some verification. So in the end, did I get the most of my training data? I'm done with training. Am I done with the neural network design, or shall I pick another or add another layer? Is there some functional verification there, and there's some semantic verification. So this is very interesting. We will come to this. What are we doing there? This V model is in that standard, part 5. We are taking a lot of knowledge from, for example, research in KI-Absicherung. That was a big project which came up with, I don't know, almost, it's over 70 metrics, what you can do and how to apply, and which metric helps for what. And there are research projects like KI Wissen that came up with how, if I have formalized knowledge, how can I put it into a neural network? How am I ensuring that it's in there, and how do I get it out to compare it to the original formalized knowledge? There are things to do. So time is almost up, I think. I can't dig into the details here. But read the standard. Anyways, what we do is, in the end, we want to say, okay, our AI system, our automated car is safe to be used within a certain domain, operational design domain. We take this table we saw it before with the systematic, random, and uncertainty-related activities, have it as an evidence or an argumentation base, feed it in a hierarchy of maybe GSN, so goal structuring notation, safety argumentation, and then come up with no unacceptable effects on providing safe behavior. It's a little bit of future, but yeah, we are close to really do this. So neural networks are there somewhere in between hard and software. So Oscar, you are getting up. How many seconds? 3. Okay. So what we did here in this working group is that we started at the highest level, the solution level. We were clear that looking at the car is not enough. And we were setting up like these 6 parts, terms and concepts, management. You will be very familiar if you went through the 2622, except for that we have the solution level, which is the driving environment, user, and all stakeholders. Actually, this is a level where hazards happen. No hazards, only failures in the levels below. We can discuss this later. We took the safety lifecycle, included multi-aspects risk, trustworthiness, system of systems, system engineering, AI as a new technology, and came up with the standard. So if you use it, think of AI and safety. It's no more burden. And this standard helps you, if you implement it, to really have fun again, even with standards. Yeah, so after all, keep AI in the systems. Don't work around and do classical stuff. We can make it safe. It's a little bit of effort, but we can make it safe. Of course, one of the factors is the data. We still need the old good automation and systems engineering knowledge. The AI is not doing it for you. You need to identify which component is done with AI and which functionality. And we have to consider the fault models. What does it contribute, the component with AI, to the hazards? Thank you.